All right. So last time we finished up talking about some properties and determinants, and started talking about some applications. We really hadn't done any real application yet of determinants. We had just came up with that formula that that we could take the inverse of a matrix using the adjoint. How do we define the adjoint again? Yeah, transpose of the matrix of cofactors, right? And what is a cofactor again? How do you get a cofactor? So if I start in row I, column J, how do I get the cofactor associated with that particular entry? What do I do? Good. You have to take the determinant after you, and then you'll also have to worry about the sign in front, right? Whether it's a positive or a negative. Good. So adjoint is that transpose of matrix of cofactors. So again, to get your cofactors, you remove row I and row J, take the determinant, and then worry about if it's an even or an odd permutation kind of idea. If the row plus the column number is even, you make it positive. If it's odd, you make it negative. All right. Okay. All right. Pardon me. So then we have the inverse formula using the adjoint. Just to rewrite that back down again. If your matrix is invertible, how can you get the inverse? 1 over the determinant times the adjoint. Good. All right. Cool. All right. So we're going to use this to help us come up with another rule for solving, or another way to solve systems of equations, as referred to as Cramer's rule. Okay. So we've got this. Let's look at this 2x2 system. We'll write the system here generally here in a second. We'll write the solution to the system generally here in a second, but let's see if we can do it for the 2x2, see what's going on, and then write the general rule. So we've got this system, 3x minus 2y equals 4, and negative 2x plus 5y equals 1. If we want to write this in matrix form, how would we write this in matrix form? 3, negative 2, negative 2, 5, and then what will we multiply it by? xy, and on the right-hand side we would have 4, 1. Good. So one way we talked about being able to do a solution to this system was that if I knew what the inverse of this matrix is, then I can multiply it to the other side, right? And then multiply by the inverse on both sides, and then do the multiplication on the right-hand side, and that would give me the answer, right? So notice that for a 2x2 system, the inverse is pretty easy, right? Or sorry, 2x2 matrix, I said system. How do we find the inverse of a 2x2? What do we do? Yeah, 1 over AD minus BC times, you flip your main diagonal and, negate the off diagonal, right? Okay. What do we get here? 11 on the bottom? If I did my arithmetic right. Well, notice, what's a better name for this 11? What did we do to that matrix and put this 11 in the denominator? It's the determinant of that matrix, right? Notice that fits part of our formula that we had over here for the adjoint, doesn't it? The 1 over the determinant. Look at your original matrix here. If I eliminate row 1, column 1, I'm left with what? 5. There's your cofactor there, right? Okay. If I eliminate row 1, column 2, here's my cofactor here, isn't it? All right, it's down there. And remember, again, we do the transpose of that. So that entry ends up being where? That was row 1, that ends up being down here, doesn't it? In the same spot. Now, why is it positive? Well, I did row 1, column 2. It's a negative in that case, right? Because 1 plus 2 is 3. It's odd. I'd make a negative on that one, right? Likewise, if you do 2, 1, we're left with this one, right? But again, we do the transpose, so that ends up in the same spot, but we make it negative because it's in the negative spot. And then finally, for the last one, oops, trying to erase some of these extra lines that I have flying everywhere. Finally, if I do eliminate row 2, column 2, I get the 3. That's why it ends up down here. And it was a positive. So notice that formula that we're coming up with, that we came up with a while ago for the inverse of a 2 by 2, is a special case of this adjoint formula for the inverse. That D, negative B, negative CA that we used, right? Flip the main diagonal, negate the off diagonal, is just the adjoint of the 2 by 2. Okay? So, looking at what we have over here, if I want to solve this system, I would multiply both sides by the inverse. So I have 1 over 11. And then I would multiply by the matrix by 5, 2, 2, 3. And then times a 4, 1, right? We agree? Okay. All right. Now, without putting the 1 over 11 through, I want to write it out longhand for what each entry would be. Okay? So longhand, what each entry would be, is I would have 4 times the 5 plus 1 times the 2, right? Row 1 times that single column. And then the other one, we'd have 4 times 2 plus 3 times 1. Now, why did I do that? Let's consider this matrix. The 4, negative 2, 1, 5. What's the how would you take the determinant of that matrix? Not a trick question. How would I take the determinant of that matrix? 4 times 5 minus 1 times negative 2. What I have here? Maybe a plus 2, right? When I do the minus a minus, right? What if you took this matrix this way and put the 4, 1 here? What would the determinant be? The 3 times the 1 and the 4 times the negative 2, right? And I would add it. And notice that's this one, isn't it? How did I form these two matrices? Look at the original matrix that we had. How did those two matrices get formed? What did I do? Say it again.
You replaced the 3 with the 4.
Okay, I replaced the 3 with the 4. And in the first one, I replaced the 3 with the 4 and the negative 2 with the 1, right? So I took out the first column and put in the constants, right? What did I do in the next one? I took out the second column, did the same thing, right? We agree? Okay. All right. Notice what happens here. Pardon me. We said this was the adjoint, correct? So this is your, pardon me, goodness. So let's think about how your adjoint is formed and see what we're doing here. Remember, your adjoint is your C11 goes this way, and then you go C12, C13, all the way down to C1n, right? And then this is C21, 22, 23, 2n, and you keep going, right? So this one would be CN1, CN2, CNN, this way, right? We agree? Okay. So what would happen when you multiply this by, when I multiply this by that constant vector on the right-hand side? I'm not worrying about the 1 over the determinant in the front, by the way. I'm just worrying about what happens when you multiply by the constant vector. Well, it doesn't matter what row you're in. Notice that the row number here on your adjoint actually corresponds to the column of the original, doesn't it? Right? Okay. So when you take whatever this is, if I do row I, when you do the multiplication in the ith entry here, you're going to have a B1 C1I, a B2 times a C2I, all the way out to a Bn times a Cni. Right? When you were in row I, notice which number is changing. Which numbers are changing is the column number there, right? Okay. That's what we get in that, don't we? Now remember what these are. These were the cofactors from your original matrix, the A matrix, right? And again, when we get the cofactors, what do? We take out the row and the column, don't we? So this takes out row 1, column I. This is row 2, column I. Row n, column I, isn't it? Yes.
Wouldn't it be the opposite? Or wouldn't it be column 1, row I?
Well, remember that it's when we write it down, it's in the transpose, right? But these numbers here correspond to the row and column number of the original matrix. So it's still row 1, column I of the original matrix, row 2, column I of the original matrix, and so on down the line. The subscripts still refer to the same column, row and column number of the original.
Yeah, but I thought we was worried about row I right now. I is referring to the row.
The I is referring to the row of the adjoint matrix. I'm trying to correspond it back to the original. Yeah. Okay. All right. So in any event, this is row 1, column I, row 2, column I, and so on down the line. So if you think about from the determinant, I've expanded along which column? I, right? And then these would be your coefficients, correct? So these cofactors here, the C1I, the C2I, the Cni, would be the same cofactors in your original matrix. What we're multiplying out in front by are the constant numbers, right? So when we do this, what we'll refer to as Cramer's rule is that what each of these entries are here are just determinants when you've taken out the appropriate column and replaced it with the constants. Okay. So this entry here, the first entry is determinant of, I'll call it A1, determinant of A2, determinant of an, where your A sub I is the matrix A with column I replaced by the vector B. Just go through it again, okay? So remember, when we do our cofactors, I think it'll be more illustrative with a bigger example here in a second. Okay? But when you do your cofactors, we do the transpose, right? But so as we're going across a row in the adjoint, we're really going down a column of the original. Because it's the transpose of the matrix of cofactors, right? So as we go across the row of the adjoint, we're really going down a column and computing each of the cofactors. Okay? So this is the cofactor. That's at row 1, column I, and then row 2, column I. So I'm staying in the same column, all the way down to row n, column I. Okay? Remember how we form those is take out that row and column that's associated with that entry, correct? So when I replace that column with the B's rather than the original A's, I'm getting a different determinant. And it's literally the exact same matrix except take out column I and replace it with the constants. So then what your solutions become for Cramer's rule, and I'll write this down in the next part here. So when you have the system AX equals B, your solution to this system can be thought of as the following. I can do determinant of A1 divided by determinant of A. The next one is determinant of A2 divided by determinant of A. All the way down to the determinant of AN divided by the determinant of A. And again, where AI is the matrix A, oops, bless you, with column I replaced with B. Okay. So for a 2x2 system, it's pretty fast. 3x3, it's not so bad either. You get bigger systems, it takes a little bit longer unless you've got lots of missing entries. All right. So let's do this one. What's your matrix A? Okay. Then we also have three more matrices. We've got our A1, our A2, and our A3. What's A1 gonna be? What's the first column of A1 gonna be? Okay. And then the other two columns stay the same. Reading it by columns, what's your A2 going to be? Okay. Okay. And then finally, reading it by columns, what's your A3 going to be? Yeah, okay. So again, here's A1. We take out column 1 and replace it with the B. Here's A2. You take out column 2 and replace it with the B. Here's A3. You take out column 3 and replace it with the B. You see how these are corresponding to the original matrix? All right. We're okay with where we got the original matrix from, right? That's just the coefficients from your x's, your x, y's, and z's. Literally, all you're doing is taking the constant column and sticking it in for each of the three columns. So Cramer's rule now says take the determinant of these four matrices. Okay? I've got three variables to start from, to solve for, I mean. We have three variables we need to solve for. The determinant of A is what's going to go on the bottom. And that's because with Cramer's rule, again, we're going to divide each of the other determinants by that other determinant. And that determinant that's in the denominator comes from the fact that that's the adjoint formula for the inverse. Right? It's 1 over determinant of A times the adjoint, right? So that's where that determinant of A in the denominator is coming from. Okay? So we need to do each of these determinants. You got lots of different ways to do it. I'm just gonna expand along the first row. Oops. if I expand along the first row of A, what are your minors, or your minor is going to be there? Okay, and the next one will be.
It's your first row.
Yep, first row. Yep.
1, 2, negative 5, 1.
Good. And the last one.
1, 4, negative 5, 2, 2.
Good. Let's see. 4 plus 4 is 8 times 2 is 16. 1 plus 10 is 11. Maybe times a 1. And then negative 2 plus 20 is 18, but it'll be a negative. So we get 9. If I did my arithmetic right. There aren't many good columns to expand along right here, right? Columns or rows, so I just used the first one. Okay. Remember, there's also that other shortcut you could do with a 3x3. It only works for a 3x3, so I'm hesitant to do it all the time. Remember what the other shortcut was I told you the other day? Yeah. So repeat those two, the first two columns, and then I've got 3 diagonals going down this way and 3 diagonals going up that way, and do those products. So you would have 2 times 4 times 1 is 8. Negative 1 times 2 times negative 5 is 10. Negative 1 times negative 2 is 2. Those are all positive products. The other way, negative 5 times 4 times negative 1 is positive 20, but I would subtract those. Negative 2 times 2 times 2 is negative 8, but again, I subtract those. And 1 times negative 1 is negative 1, but I subtract that. And hopefully I get 27 again. Or 9, I mean, again. Is it? Good. Yay. It's just a shortcut to do it that way. Literally, this only works for a 3x3, by the way. That's why I'm hesitant to show it, because students want to try to do it for other types of matrices. This only works for a 3x3. That's why I typically don't show it. All right. What about your other determinants? I need to do my A1, my A2, and my A3, right? Okay. By the way, I'm a lot more willing to show this one than what they refer to as the basket weave method. I'm going to show it real quick to show you why I hate it. I don't even remember how to do it correctly. That's how much I hate it. Basket weave. Well, I need to do this one. I need to do this one, and I need to do this one, and then you do the other ways. Yeah, it's ugly. Yeah, you'll never see me write that again. Okay. All right. Anyway, I need to do my A1 here. You want to do it with the rewriting the columns, or you want to do it with the cofactors? I don't care which, but tell me which one you want me to do it. Cofactors. Again, doesn't really matter what column or row you expand along, but let me expand along the first column in this case, just to illustrate what's going on with that rule with the adjoint. So your coefficients will be a positive 1, a negative 1. Oops, forgot to write my matrix in there, my minor in there. A negative 1 and a positive 2. And then again, since I'm going down the first column, your signs will be plus, minus, plus, right? The minor associated with the 1 is what?
4, 2, negative 2, 1.
Good. 4, 2, negative 2, 1. Good. The negative one, going down the first, we're going down the first column, the ones I have circled in red there. Good. And then what's the 2? Good. All right. Now, why did I want to do that? I illustrate it this way. All right. If you would have gone back to A and expanded along the same column, what would your not the coefficients obviously would change, but what would your minors look like? The same, right? Because notice that this part of the matrix hasn't changed, correct? Okay. So the minors are the same. So that's what I was saying earlier about these cofactor entries. You're getting the exact same type of determinant that you would have been from A, except that your coefficients in front have changed to be the coefficients that are coming from your constant vector. Okay. So what do we get when we do all of those? Negative 17? Yeah, sure. I'll believe you. Okay. What's that? Oh, okay. Well, I didn't do it, so more people are saying 9, so I'm going to say it's 9. Sorry, Dawn. Yeah. We choose any row or any column for cofactor expansion, correct? Remember, the cofactor expansion is just keeping track of all of the possible permutations you can do without repeating rows or columns. So that's why you can do any row or any column you want. Yes.
So, why did you choose column 1 for this A1? You just chose it just because that's what.
I just chose the first. Yeah, the only reason why I chose column 1 for A1 is just to show what was going on, that the minors aren't changing. The only thing that would change with your determinant is those coefficients in front. But you could have literally done any row or column you wanted to. Yeah. All right. So that would be your A1. Was unnecessary for this particular problem, because notice it's saying they solve for only Z, right? What would the A1 and the A together give you? X, right? So from those two values, you should be able to tell me what X is, right? What is X equal to? 1. Good. Yes.
X. Could you explain
Why X is?
9 over 9.
It's determinant of A1 over A. That's the rule. Yeah. It's because, again, it's coming from the adjoint formula for the inverse, right? I'm taking the adjoint times the B. It's giving that determinant of A1 on top. So we should be able to do the same thing for the other ones. Did anybody get the determinant of A2 without having to write it all out? Okay, cool. And A3? 27? Cool. All right, so what would Y... I assume that at this point you can do those. I hope. So what's Y going to be? -2, good. And Z will be 3. Kramer's rule is nice if you've got a small system, or if you've got a system where you've got lots of zero coefficients on variables, so that the determinants are easy to compute. If you've got larger systems with lots of coefficients, you're not going to do the solutions this way. If you have like a 5 by 5, if there's lots of zeros, Kramer's rule might be nice. But if it's, you don't have any zeros entries at all, it's just so computationally expensive, you're not going to do it that way. You would use something with row reduction instead. The main reason why we show this is because you will see it for anybody who wants to do engineering types of things. You'll see it in engineering classes. It also tends to be on certification exams. So that's why I showed it to you. I mean, it's a cool little rule. It works really well for 2 by 2, right? Because I can just do the products real quick and be done. Okay, the 2 by 2 is really nice. 3 by 3, nah, it's okay. Right, get much higher than that, you're gonna be doing products all day long. Also, Kramer's rule require what are the big limitation of Kramer's rule. Kramer's rule does not work if the system's not if you don't have a square coefficient matrix. It has to be squared. It has to take determinants, right? It also doesn't work if you have no solution or infinitely limited solutions. The reason why it doesn't work is because if you have no solution or infinitely many solutions, what's the determinant of your coefficient matrix? What's your big clue when you row reduce that you have no solution? You got a row of zeros. What's the determinant going to be? 0, right? You can't divide by it. Okay. So those are the limitations for Kramer's rule. Has to be a square coefficient matrix, same number of equations as variables, and you have to have a unique solution. Okay. If your matrix isn't invertible, it doesn't work either. So those are the kind of the two big limitations, besides the fact that when you get large systems, it's computationally expensive. In any event, that's Kramer's rule. It's kind of, like I said, it's kind of a fun little rule. Works nicely if you've got a smaller system or lots of zeros, but other than that, you're not going to use it. All right. So let's go on and talk about some other applications that you can do with determinants. Not a huge surprise that you can do areas with determinants, since that was kind of how we motivated things, right? With areas and volumes, right? But if you've got 3 points, you can figure out the area of the parallelogram that would be determined by those, or just literally the vertices of a triangle. And it turns out that the area here will be 1/2 times the determinant of the following matrix. You can put your points in along with a 1 down the column. And actually, it doesn't matter where you put the ones, by the way. You're going to put the ones in the middle or put the ones in the front. The book just writes it on the end. Turns out to be 1/2 of that. Almost. We know that it depends on the order you put things in, that it might be a plus or a minus, right? So you might need to take absolute value if it's negative. I'm hesitant to put plus or minus because it can't be both, right? If it's negative, you just make it positive, make the area. Okay. Why does this work? Well, if you were going to do you remember that row operations don't change. If I do a row operation where I do a constant multiple of one row and add it to a second row and replace that second row, it doesn't change the determinant at all. If I start with this matrix and do negative row 1 plus row 2 replace row 2, and the same thing but do it with row 3. That doesn't change row 1. What does row 2 become? Let's see, x2 minus x1, y2 minus y1, and 0, right? And then likewise, the third row looks almost the same, right? And now if you expand along the third column here, all we end up with is this matrix, this determinant, isn't it? Right? If I expand along this column, there's got 2 zeros in there, so the other ones are going to go away, right? The coefficient you would multiply is by a 1, and it would be positive given where it is. The only thing I'm left with is this submatrix right here, right? That's the only thing we're left with. Okay. We agree? All right. Why did I do that? Good question. Say I have 3 points. If I want to start at x1, y1 and go to x2, y2, how do I get the vector that goes from x1, y1 to x2, y2? What do you do? If I want to start at x1, y1 and go to x2, y2, what do you do? You subtract x2. Yeah, this would be x2 minus x1, comma, y2 minus y1, isn't it? Likewise, if this is x3, y3, again, we just subtract again, don't we?
Yeah.
If you want the area of the parallelogram determined by those 2 vectors, you take the determinant, don't you? It's the determinant of that, isn't it? Right? So forming your this 3x3 determinant here is the same thing as forming your 2x2 determinant here. You get the same value. Why do we do a 1/2 in front?
Triangle.
It's a triangle. It's half the area of the parallelogram. Right? That's where the 1/2 comes from. So this formula isn't anything different than what we've already talked about. It just saves you from having to do the subtractions to start with. Okay. Just make sure that you do absolute value if it turns out to be negative. Right? We can expand this up a dimension if you've got what's referred to as a tetrahedron. A tetrahedron is a 4-sided solid with all triangles on it. Okay? You can do the volume in a similar fashion. You're going to create a 4x4 determinant. Create a 4x4 matrix, take the determinant. Without a coefficient in front, that's going to be the same as that parallelopiped or parallelepiped, depending on whichever way you want to pronounce it, that we talked about, where you can have 3 vectors and makes a solid. Turns out that if you divide it up into just the tetrahedron part, there's actually 6 of them in there. So you'd have a 1/6 out in front. For the tetrahedron, you'd have a 1/6 that goes out in front because you can split it up into 6 parts, 6 congruent parts. Yes. For the area, it's a 1/2 out in front because it's half the parallelogram. When you've got 3, I can do the same kind of picture in 3 dimensions. I'd have one vector, say another vector going backward, and another vector going up this way. And so then you've got something that looks like this. It's basically looks like a box has been sheared. It wasn't bad for drawing it quickly. I've drawn worse pictures. I've probably drawn a worse picture today. Okay. You can divide this up into 6 pieces, 6 congruent pieces. Okay, that's where the 1/6 comes from. And again, you might need to take the absolute value if it turns out to be negative. Okay. All right, so let's do a quick example with numbers. So say we want to find the area of this triangle. I'll do a 3x3 determinant. What's the first row going to be?
1, 3.
First row?
1, 5.
Maybe 1, 5, 1, 3, 8, 1, 4, -3, 1. Good news is that if you would have gone down the columns, you would have got the same answer because you've been taking transpose, which doesn't change the determinant. Good news is it's really, really hard to screw it up as long as you keep things together. Okay. You can put this column of 1s here, here, or here, or you can take the transpose and make a row of 1s. As long as you keep things together, you won't screw it up. one of the reasons why, all right, so there's two reasons why you won't screw it up as long as you keep things together correctly. One, all a row or a column swap does is make it positive or negative. It doesn't change the absolute value. And we're going to take the absolute value at the end anyway, right? Taking a transpose doesn't change the determinant either. So it doesn't matter if you go points across and make a 1 or points down a column and make a 1 at the bottom. It doesn't matter. It's really, really hard to screw it up. Okay? You'd have to start mixing and matching coordinates of points to screw it up. Yes?
Did you say that we'll have to take the absolute value?
Well, at the end, if it turns out to be negative, you have to take the absolute value since you're doing an area. All right. So again, here doesn't really matter how we do it. I'm going to expand along this column with 1s because multiplication by 1 is relatively easy. So I'd have 3, 8, 4, negative 3, and then a minus 1, 5, 4, negative 3, and a plus 1, 5, 3, 8.
So you don't gotta reduce early.
You can. You just don't have to. You just have to take the determinant. The only reason why I row reduced earlier was to show you that it really is giving you the same value that we talked about when we started determinants. But you don't have to do the row reduction. Or you can. Either or works. Doesn't matter. Whatever way you want to do it is fine. Okay. Negative 9 minus 32. Minus 41. Negative 3 minus 20 is negative 23, but we'd be adding it. 8 minus 15 is negative 7. What is that? Negative 25. Right? That, I didn't put the 1/2 in front of it either, did I? All right, so the area here would be a positive 25 over 2. I need to make it positive because the area can't be negative, and I need to divide it in half because this determinant really just figures out the area of a parallelogram. Questions on that one? All right. Let me ask you a really hard question. If all 3 of those points had been on the same line, what would the answer have been for your determinant? If all 3 points had been on the same line, all 3 points that you were given had been on the same line, what would your determinant have been? 0, because there wouldn't have been any area, right? So, using that same kind of concept, if you want to find an equation of a line through 2 points, well, remember your equation of a line needs to satisfy some condition on the x and y. Well, if some arbitrary point x, y needs to be on the same line that these two are, what should this answer turn out to be when you're done? If an arbitrary point x, y is going to be on the same point as these 2 points, what should this answer turn out to be when you're done? 0, yeah. So this is another way that you can figure out an equation of a line between 2 points. You can do it with determinants. And again, all we're using there is the concept that if I put in some value for this x and this y, I better not get any area. They all better be on the same line. We can do the exact same for the same thing for a plane. If 4 points are going to be on the same plane, what would be the volume of the tetrahedron formed by those 4 points? That would be 0, right? So again, here you would do x, y, z, 1, x1, y1, z1, 1, x2, y2, z2, 1, x3, y3, z3, 1 has to equal 0. And all we're doing here is saying that the same idea for a line. If you've got 4 points, but there's no volume, then they must all be on the same plane. That's all that's saying.
So if they're on the same number.
No, it'll all be the same number. This means they're all on the same plane, right? Yeah, so it's just flat. Yeah, it's all it's saying. Yeah, there's just no height to it at all. Yeah, the fourth point's not doing anything. So let's go back up here to this particular example. Here is 1, 2, 3, 4 points, right? All I'm saying is what happens if this point were actually down here?
So
There wouldn't have been any height to it at all. You would have just been in the plane.
how would you put that like in actual case?
How would I put that in an actual number case?
Like would it be 1, 5, 3, 8, and like 1?
Well, I mean, these are be 3-dimensional points. So you could do like, I could do 1, 0, 0, 0, 1, 0, 0, 0, 1, and then do 1, 1, 1.
Oh, okay.
Yeah. I could do something like that, and then there wouldn't be any height to it. Okay. Okay. All right. So just to do this real quick for one of these, if I want to find the equation that goes through those 2 points, I can set it up this way. I'd use x, y, 1 as my first column. Oops. -4, or sorry, I said first column, I meant first row. -4, 2, 1 is my second row, and 7, -5, 1 is my third row. That has to equal 0. I'm going to switch it up a little bit and expand along the first row in this case. What would your x be multiplied by? 2, 1, -5, 1. What would your y be multiplied by? And what would the last 1 be multiplied by? And again, that has to equal 0 on the end. The only reason why I expanded along the first row, do you see any x's or y's in my determinants now? No. That's why I expanded along the first row. I left the x out in front of the first one, the y out in front of the second one, and then the third one just has a coefficient of 1 on it. Okay, so that was why I expanded along the first row. You can do whatever you want. Just know that you're going to have a variable in some of them, and you'll have to combine like terms. Here I don't have to combine any like terms when I'm done. I have my coefficients already for me. What's the coefficient on the x? 7. Coefficient on the y? It'd be a positive, right, when we're done, because I got the negative in front when we expanded the determinant. And then finally, your constant would be 6. There's your equation of your line. That was why I expanded along the first row. I didn't have any combining of like terms I had to do. All the x's are in the first determinant, all the y's are in the second, and my constant's on the end. Is that okay? You can do the exact same thing for the plane. You've done, well, if you've had Calc 3, you've done equations for planes, right? You probably haven't done it this way. All right, you probably started with 1 point, found 2 vectors, and then did a cross product to find a normal vector. Yeah, this is just a single determinant and you're done. A little bit nicer than that, isn't it? Okay, all right. All right, well, let's start a new section on Friday. So have a good one. We shall see you then.